Have you ever wondered how electrons are arranged inside of an atom? Today, we're diving into electron configuration and orbital notation, the keys to understanding how atoms behave, bond, and form the world around us. By the end of this lesson, you'll know how to write electron configuration step by step, use orbital diagrams to visualize electron placement, and even predict chemical properties just from the way electrons are arranged. The atomic nucleus is extremely small compared to the entire atom, being roughly 100,000 times smaller in diameter. Imagine the atom as the size of a football stadium. The nucleus would then only be about the size of a pea on the 50-yard line. Most of the atom's volume is empty space, with electrons occupying the vast region around the dense nucleus. Since the nucleus are on the outer part of the atom, we need to describe what is called the valence electrons. These are the electrons in the outermost part of the atom. These are the key players in the chemical bonding. Only the s and p orbitals of the outer shell are known as valence electrons, which means that I have 2 plus 6, which means generally we have no more than 8 electrons in the outer shell. Atoms form chemical bonds because their resulting electron arrangement is more stable, often resembling a full outer shell. So I can have two types of bonding here. I can have ionic bonding as well as covalent bonding. So for ionic bonding, electrons are transferred, okay? So the atom which loses an electron becomes positively charged. Okay, and this positive charged ion is called a cation. The atom that receives an electron forms a negative ion, and it's called an anion. So we also have covalent bonds. This forms between two atoms which share a pair, two pair, or even 3 pairs of electrons between them, forming either a single, double, or triple bond. When describing reactivity, atoms which have like 1 electron in the outer shell, these are very reactive metals. So they're very unstable because they have only 1 electron in the outer shell. Or if I have 7 electrons in the outer shell, they're also very reactive. Because they both want to achieve a full outer shell. Trends depend upon the number of electrons in the outer shell. Things such as the size of the atom, its ionization energy, its electronegativity, and many other features depend upon the number of electrons located in the outer shell. So in this lesson, I'm going to show you how to write electron configurations, both the long form and the condensed forms, draw orbital diagrams, and predict properties. Before we get started, let's look at a simple diagram showing you the locations of the s, p, d, f orbitals. Notice that the first shell has only s orbitals. The second shell has s and p's, which gives me 8. The third shell has s and p's, and then it doesn't fill immediately. The d block fills one shell from the outermost. So I must add electrons to the s orbital in the next shell before coming back and filling the d block. The f block fills 2 shells from the outermost. Metals are to the left of this zigzag line. And nonmetals then would be on the right side. Metals tend to lose electrons. Nonmetals gain electrons. Okay, so you would think then that metals will form positive cations and nonmetals will form negative anions. The Aufbau principle helps you to put your electrons in the proper order. All right, so first of all, we have 1s electrons, filled then by 2s, then by 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, and 7p. This is the order in which the electrons will fill. It's called the Aufbau principle. This is very important to know. In our first example, we're going to write an orbital notation for aluminum. Aluminum has an atomic number of 13, which means it will also have 13 electrons. 1s has an up and a down electron. That gives me 2 electrons. Okay, 2s, I have an up and a down. Okay, and 2p has an up, and up, and up. Hund's rule says you will put 1 electron in each of the orbital's sublevels before pairing them up. We're shooting for aluminum which has 13 electrons. So we need to keep going. Okay, so that gives us 8 in that shell, so that's 10 electrons. So we need 3 more. 1, 2, and 3. All right, so this gives us a total of 13 electrons. So this will be the orbital notation for aluminum. If I want to write the electron configuration for this, I'll say that 1s has 2 electrons, 2s has 2 electrons, 2p has 6 electrons, 3s has 2 electrons, 3p has 1. So this is the electron configuration. For aluminum. Now, if I want to write the shorthand method, I find aluminum on the periodic chart, and I go up and over to the end of the previous row. So at the end of the previous row, we have neon. If I place neon in square brackets, that will be my reference point. So this is neon here in the square brackets. So I would simply write neon in square brackets, followed by 3s2, 3p1. So this is the abbreviated way of writing the electron configuration for aluminum. And since aluminum has less than 4 electrons in the outer shell, that has only 3, you know it's a metal. And you know it's not superactive because it has so many electrons. In our next example, let's write the orbital notation for bromine. Bromine has an atomic number of 35, so therefore it has 35 electrons. Okay, I found bromine on the periodic table, and I can locate its location. It's in 4p. I know I'm going to stop when I get to 4p here. I can basically fill it in until I get there. So I go 1s, 2s, 2p, 3s, 3p, then I go 4s, then I leave 4s and I go to 3d, okay, and 4p is bromine is the fifth one. So that will be the orbital configuration or orbital notation for bromine. So let's write out the electron configuration. So it can be 1s, 2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Or if I want to write the shorthand notation, I go up and over to the right to argon. So this represents argon here. All right, so 4s2, 3d10, 4p5. This is not considered exactly correct. Generally, the accepted method is to arrange these in order from inside outward. Since 3 is smaller than 4, the accepted method will be argon, 3d10, 4s2, 4p5. Since this has 7 electrons in the outer shell, you know it's going to be a very reactive nonmetal based on the electron configuration. In this example, let's try iron. Iron is a transitional metal with 26 electrons. It is located in 3D. So I can go ahead and start filling these in. Okay, so it's 1, 2, 3, 4, 5, and 6. So that's the orbital notation for iron. So the electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay, the end of the previous row will be argon, and that's argon. So I'm going to place argon in square brackets, and I'm going to list them 3d6, 4s2, like this. So notice that iron has only 2 electrons in its outer shell. So let's try iron with a positive 2 charge. So what would happen here? Okay, so we have a positive 2, so that means you have 26 electrons minus 2 electrons gives me 24 electrons because it loses 2 electrons to become positive 2. So which electrons does it lose? Does it lose the S's or does it lose the D's? Okay, let me show you. So I'm going through filling in each of these orbitals with its proper number of electrons. So I got my 4s. All right. So which electrons does it lose? Well, it's going to lose these electrons here. Okay. So when I go to write my electron configuration then, we'll see it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d6. And you don't have to include this 4s0. So you can leave that out if you like. So look here. Okay, so that's argon. There's argon 3d6. Or if you like, you can say argon 3d6 4s0. Either one's correct. Okay, let's try the oxide ion, which is oxygen, which has 8 electrons, and it's going to gain 2 more electrons, so that gives us 10 electrons. So we go 1, 2, 3, 4, 5, 6, 7, 8 electrons. I'm going to add 2 more, 9 and 10. So oxide is 1s2, 2s2, 2p6. So that gives me a total of 10 electrons. On a lot of tests, especially standardized tests, they like to include some exceptions. So let me show you 2 exceptions. One is chromium. Chromium has 24 electrons. Okay, chromium is located within 3D. All right, so let's go through. Let's add our electrons. After 4s, I go 1, 2, 3, 4. That's 24 electrons. It has one empty space here. By having one empty spot there, it makes it less stable. So what happens is, this electron in 4s will come down and fill here. I'm removing one electron from 4s and placing it into 3D. So now I have a half-filled 3D, which is a half-filled orbital is stable. But an orbital that lacks one electron is generally not as stable. So usually full orbitals or half-filled orbitals are the ones that are most stable. So to write this configuration, we will say that it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Or I can say argon 3d5, 4s1. That would be my answer. The other very common exception will be for copper. So copper has 29 electrons. I'm not going to fill all this in this time. I'm just going to go up here to 4s. It has an up and a down. Then we go to 3d, which is an up, 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 and then a down, a down, a down, and a down. So I'm missing one down electron because it has 9 electrons in the outer shell, and it requires, or it wants 10. So again, it's going to borrow a 4s electron. So it's going to basically take this 4s electron, and it's going to pull it down here. So we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So we can say 3d10, 4s1. Okay, these are the 2 exceptions that you generally see on standardized tests. So make sure you're aware of those. There are other exceptions in 4D, 5D, 4 and 5 else, but these are the 2 that most teachers require that you know. Okay, let's try a really large atom, bismuth. Bismuth has 83 electrons, okay? I noticed that bismuth is located in 2p, 3p, 4p, 5p, 6p. So I know I'm going to end here in 6p. Let's fill it in starting at 6s. So if I start at 6s, when I leave 6s, I go to 4f. When I leave 4f, I go to 5d. Then when I leave 5d, I go to 6p. And it is the third one. So electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p3. All right, so this is the end of the previous row. So it would be xenon. Okay, I'm placing these in the proper order. 4f comes first, 4f, 14, followed by 5d, 10, 6s2, 6p3. So that'll be the answer to that one. Thank you for watching. Please like and subscribe, and I'll see you again very soon. Goodbye.